Hello, welcome back to Math 332. Today we are going to look at several more examples on how to apply Theorem 4.2.1, which is how do we determine whether or not a subset of a vector space is itself a vector space. So Theorem 4.2.1 says that if you have a vector space V and then you have W, which is a subset of V, how do we determine whether or not W is not only a subset of V, but itself is also a vector space. So if W is a vector space, and because it sits inside V, which is a vector space, then we say that W is a vector subspace of V. All right. So we don't really have to go through all the 10 axioms because V is a vector space. So so those 10 axioms, a lot of those axioms inherits by elements in W. So in fact, in order to verify, to check whether or not W is a vector subspace of V, there are only two things you have to do. Well, technically three. The first thing you have to do is to try to make sure that W is not an empty set. And then once you have done that, you pick two elements from W, and then you try to add them and see whether or not the addition here still will be in W. So we want to check whether or not the addition is closed in W. And also you're going to take an element, a real numbers, okay? So you're going to take a real numbers, pick one of the elements in W, and see whether or not this scalar multiplications is still in W, which means that we want to see the W is closed under additions and also closed under scalar multiplications. Now we can do that, then W is not only a subset of that vector space V, but in fact also a vector space, hence a vector subspace of V. All right, let's look at the first example. We are looking at the vector space consists of all the 2 by 2 matrices, of course, with the usual matrix additions and the usual matrix scalar multiplications. And now let's look at W1. All right, so W1 is a subset of V. Now, a lot of time you really have to understand what is W1? What is a set means? What is that set? Okay, so the way you look at it, so this is a set builder notation. So here they will try to tell you what are the elements, and here they will try to provide extra information, the descriptions of the elements that is here. All right, so as you can see, so the way you read it is, first of all, W1 consists of all the 2 by 2 matrices, such that if you pick one of the matrix A and you look at the system of equations, okay, you look at the system of equations and see whether or not the solutions, does it X really has to be 0, Y really has to be 0. If X equal to 0 and Y equal to 0 are the only solutions, then we say is that the system has only trivial solutions. Okay, the obvious one. Trivial solutions means the obvious one. And if you can find some of the other solutions, for example, X equal to 1, Y equal to 0 is also a solution, then the systems has non-trivial solutions. This is the non-trivial solutions. Okay, so for example, I claim that the identity matrix 1, 0, 0, 1 is in W1 because if you look at the system, so if you look at the system equations, so X and Y, these are the unknown, and set it equal to 0, 0. Okay, so you have to be very careful though. I mean, sometimes the notation should be clear from the context. So this is not the 0 as a number. This is a 2 by 2 matrix, so this has to be a 2 by 1 matrix, which is our column vectors, and because of that, this 0 here is actually the columns, the vector 0, the 2 by 1 vectors, which has the entries both 0. So basically we are looking at a system that looks like this. Now, so I claim that the identity matrix is in W1 because if you look at the system, you can clearly see that there are no other possible solutions. The X has to be equal to 0 and Y has to be equal to 0, which means the only solution for the system of equations for the system right here is the trivial one. Okay, so W1 is actually in, the identity matrix is really in W1, so W1 is not empty. Now, if you are new and you are like not very sure about all this, it's very beneficial to try to figure out what are the elements, how the elements looks like. So let's pick another one. So I'm also claiming that 1, 2, 0, 3 is also in W1. Now, we already have a lot of tools to determine the number of solutions for the system. One way is you can row reduce it, and another way we can just simply look at the determinant. Now the determinant of this matrix is 3, right? Because it's a upper triangular matrix, so the determinant will be merely the product of the diagonal entries. So the determinant is 3, so it's not 0, so we know this matrix is invertible. So when you have something that is invertible, and this is a homogeneous system, so what happened is that the solution is going to be inverse of this matrix multiply this, and I don't even have to compute this because this product with a 0 0 will really just give you nothing but 0 0. So so again we get the trivial solutions. X have to be equal to 0, y has to be equal to 0. So this matrix 1 2 0 3 is in W1 because the system here, this system has only a trivial solution. So when you try to identify the elements of a set, you have to find those elements, okay, in this case is our 2 by 2 matrices that satisfy these conditions. When this condition is satisfied, then you belongs to that group, okay, you belongs to that set, okay, right. So as you can see, actually, that W1 here cannot be a vector space. Because to be a vector space, one of the requirements, one of the axioms is to require that the zero elements has to be in it, right? And as you can see, the zero matrix, the zero elements in this case is our zero matrix. Okay, so our zero matrix here does not belongs to this set. Okay, why is that so? If you look at the system of equations, and you can see that this system of equations give you infinitely many solutions. In fact, x equal to 0 and y equal to 0 are the one of the solutions, but obviously whatever things you can think of, x equal to 2, y equal to 5 is also solutions. And in fact, you can set this as equal to t, y equal to s. In fact, the system has 2 parameters. And it generates infinitely many solutions, as we have studied before. And you can see that this system here does not give you only the trivial solutions. So therefore, the zero matrix does not belongs to W1. It's not in it. You cannot find 0 0 in W1. Okay, why is it not in W1? Because it does not satisfy this requirement. All right, so because of that, it cannot be a vector subspace of M2 by 2. This is not the only way to do it, to show that W1 is not a vector subspace of M2 by 2, because you can try to show that the sets here does not close under addition also. You can pick 2 matrices that satisfy this condition and add them and show that they are actually not closed. They are not in W1 after you compute the addition of that 2 matrix. Or you can pick a number and another matrix which is in this set and show that it's not closed. They are not closed under scalar multiplication. We're not going to do it here because obviously this is kind of easy to see. So we know that the 0 elements in this set is not in W1. So W1 can never be a vector space. It's just merely a subset. All right, and hopefully you can see that it is a subset because whatever you have element here is they are all 2 by 2 matrices. So they are subsets but not subspace. Okay, now because most of you, when you don't really know how to apply theorem 4.2.1 is because you have trouble reading the set. So I'm going to give you things that kind of looks like the sets that we have seen in W1, but they are actually very different. So for example, here we have the same vector space V, but then our W2 is this set. So W2 is not consist of matrices. Oh, right. I'm so sorry. So in this case, this V here is no longer M2 by 2, but R2. All right, my bad. So now our V here is R2, and our W2 is right here. Is a subset of R2 because, as you can see, you don't even know what that thing is yet. I mean, if you don't see what are the description here, it already tells you that this set consists of all the 2 by 1 matrices, which means our column vector. So it consists of all the things that looks like this. All right, so this set W2 consists of all the elements that looks like this, Okay, so it's not a matrix anymore. So it's x1, x2, 2 by 1 column vectors. All right, so it's not all 2 by 1 column vectors, otherwise it will be the entire R2. So here, okay, so here they provide descriptions. So we are only looking at all the 2 by 1 matrices that will make the system equal to 0. For fixed A. So it's fixed. So A is a fixed matrix, okay? We didn't given what that matrix is, but we know that it's a fixed matrix. So we are actually looking at all the x1 and x2. So remember though, we are actually looking at all the x1 and x2 such that once we have a matrix A, which is here, such that this one will give you 0, 0. Okay, so we have a, but this A is fixed, and we actually do not know what that thing is. Okay, all right. So, so we want the column vectors here to satisfy this equation for whatever A that is non-zero matrix. So A could be, so if you think it's going to help you in understanding all this thing, you might be, you can actually say that, okay, it's kind of like A is like 1, 2, 3, 4. It's not a zero vectors. It's not a zero matrix. So I am actually looking at all the vectors x1, x2 that will make this 0, 0. Okay, so in this case, for example, in this case, because this matrix is invertible, just like what we discussed before, and in this case, we know that one of the solutions will be x1, x2 equal to 0, 0, and in fact, that's the only solutions because this matrix is invertible. Okay, so for invertible matrix and a homogeneous system, you have only the trivial solutions. So in this case, your W2 will be just sets consists of one element, which is the 0 element. But because since we don't really know what A is, so we don't really know, right? So we don't really know, but we actually do know one of the elements in W2. We know one of the elements. We don't really know about the other one because we don't know what A is. So one of the elements must be 0, 0 because no matter what your matrix A is, if you hit it with 0, 0, you will definitely get 0, 0. So this one here, stay in this set. This one here, stay in this set. Okay, so the W2 consists of 0, 0. At least it contains this particular one element. So because of that, your W2 is not an empty set. So W2 is not an empty set because, W2 is not an empty set because you found one element, which is this 0 elements is in W2. All right, so let's see whether or not it is a vector subspace of R2. All right, so let's take two elements. Please do not specify what those elements are because you want to prove that actually for every element in W, this property hold. Every. So you cannot argue by example. Same thing here. You have to prove that for every element here, for every element U, and for any type of scalar, this product here will be still in W. So we have to show it in full generality and not argue by example. So because of that, we take something from W2. Let's call it x1, x2. And let's take another something in W2. Let's call it y1 and y2. And because x1, x2 here is in W2, so it's not any random R2 elements, but it's the one that will satisfy this, right? So A is fixed, right? So x1, x2 in W2 means that this system will has to be equal to 0. So if you try to multiply A to this matrix, you will have to get 0, 0. Okay, so y1, y2 is in W2, means that y1, y2 will satisfy these equations, which means that if you take that fixed matrix A, which we don't know what that thing is, but we know it exists and it's fixed. So you hit it with y1 and y2 and you get 0, 0. So the x1, x2 and y1, y2 satisfy these conditions. And let's call this condition star. All right, let's call this condition star. Now we want to verify that after we add them, it is still in W2. So how do you do that? Well, let's just add them, right? Let's just add them and hit it with A and see whether or not you get 0, 0. So okay, so we put A here and then put this vector addition here to add up these two vectors. And we can actually distribute A because matrix multiplication is distributive. So you will have this, so this part here. So this part here is really equal to this, okay? Because you can distribute the matrix A. And then x1 and x2 is not any 2 by 1 column vectors. It's not any 2 by 1 column vectors. y1, y2 is not any 2 by 1 column vectors. They are the elements from W2. So if they are the elements of in W2, this part here will have to be 0. This part here will have to be 0. So the additions of these 0 vectors will give you 0 vectors. So now if you look at this thing right here, just right here, so you see that here equals to 0, 0, means that whatever inside here will be in W2 because W2 is actually looking for all those elements such that A of that thing is equal to 0. And you can see that thing in the box, that thing, okay, equal to 0, 0, and we have to collect this thing. So this thing is in W2. See that? This thing is in W2. All right, so because of that, W2 is actually closed under additions, because if you take two vectors from W2 and add them, it is still in W2. So this is how you verify something belongs to a set, while you see whether or not it satisfies the description of the set. So that's not possible for us to go through all the possibility of whether or not something belongs to a set or not. It really depends on what are the descriptions. So you really have to just know how to follow the instructions. Just follow the instructions and you will know. So in this case, we want to check whether or not A of that thing equal to 0. So if it is true, then this thing here in the box will belongs to this set. All right, so apparently they are closed under additions. How about scalar multiplications? So pick, again, same thing, don't specify what that number is. So pick a real number, okay? Let's call it K, and let's take another x1, x2. You can put the same x1, x2 that we have here from before. Key thing is it has to be in W2. So being in W2 means that this has to be satisfied. Right, now you take a matrix, if you take a number K and multiply with that, and I'm claiming that this thing is in W2 because if you do this computation here, so if you do this computation here, this is a number, this is a 2 by 2 matrix, you can take the number out. So I took that number out, and then this one here will be 0, 0 because x1, x2 are not any 2 by 1 matrix. It's not any column vectors. It is the ones that will make A multiply this equal to 0, 0. So we have that, and K is whatever number that we have from before. And this scalar multiplications really give you 0, 0. So A of that thing is equal to 0, 0. So that thing here has to be in W2. So that thing is this. So we show that, so we have shown that. Take a number K, take an element here, you multiply them, that thing is still in W2. So it's closed. So W2 is closed under scalar multiplications. So W2 is both closed under additions and scalar multiplication. So by theorem 4.2.1, W2, this W2, our little sets here, W2, is not only a subset of R2, but is actually a subspace of R2. All right, so I hope it makes sense. And let me remind you, we want to look at all these examples that kind of like similar looking, but the sets are very different. So here we do have A, here we do have A, but here the entries here, the sets are all 2 by 1 column vectors. Here they are 2 by 2 matrices. So you have to be very extra careful on reading these sets builder notations, right? Okay, let's look at the third example. So the third example, okay, so our V is R2. So now we still have the A, we still have the X, but you have to be very careful about what W3 is. So we have W3. Our vector space is R2, and this W3 is subset of it. Why is that so? Because here, from this right here, they are telling you we are actually looking at AX, okay? So A is a 2 by 2 matrix, that's what it said. And also it's a fixed non-zero 2 by 2 matrix, and X is in R2. So what are the elements in W3 looks like? Okay, so let's see. Apparently A is fixed, non-zero. So let's say, I mean, just for your understanding, we're not saying this, okay? So, but we can think of it as if A is a fixed matrix. Let's pick our favorite matrix, 1, 2, 3, and 4. So it's kind of like this. A is like this, it's fixed. But we are not, this W3 does not consist of A. It consists of things that looks like this, okay? Things that looks like this. All right, so let's look at the size. Obviously, this is 2 by 2, this is 2 by 1. So we're looking at this. So we're looking at the sub-matrix product. So we are actually looking at this guy here, which is 2 by 1. So we're looking at 2 by 1's column vectors, which is 2 by 1 column vectors, such that that's it, right? They are just looking at this. They are just looking at it. Do you see that? So we are actually looking at all this thing, okay, which is the things that you obtain after you multiply this matrix with column vectors, all the possible column vectors. So go through all the possible column vectors. So for example, if I take 0, 0, okay, so obviously you get 0, 0. So this 0, 0, not this. This 0, 0 will be in it, okay? So for example, let's take another one. So let's say we take 1, 0. So this matrix multiplication will give us 1, 3. So 1, 3 will be an element right here. You follow? Okay, so let's take another one. Let's say 0, 1. Okay, so 0, 1, so you get 2, 4. So 2, 4 will be in it. 2, 4 will be in this set. 2, 4 will be in this set, not the 0, 1. 2, 4. Okay, all right, so that's what W3 is. All right, so we can find infinitely many elements in this case, right? Obviously, so we have like 1, 2. So what this thing is, so this will be this multiplied this will give you 1, 4. That will be a 5, and this is going to be 8. So 9, 10, 11. So it will be this, right? So this matrix multiplication give you 5, 11. So let's check that again. So you have 3, you have 8, so you have 11. So 5, 11 is in this set. So 5, 11 is in this set. All right. Okay. It's not the 1, 2. I mean, 1, 2 will be, would it be or will it not be? We don't really know yet, but 5, 11 is in it. So we already have like 3 different elements in W3, right? Okay. So make sure you know how the elements looks like. So let's look at this description one more time. Okay, so what it says is, okay, we are collecting all this thing, which is element in R2, and here the A is a fixed non-zero 2 by 2 matrix. So throughout this process, as you can see just now when we are like investigating this thing, throughout this process, I didn't change this. I didn't change 1, 2, 3, 4. I didn't change it. The only thing I changed is the entries right here, x1, x2. This is the only thing I changed, right? I didn't change this, which means we are doing something that's similar to this. We are taking a matrix A. We don't know what that matrix is. We know it's non-zero. And that's the only thing we know. And we are varying all the 2 by 1 column vectors and see what do you get. All right. This is going to be similar to something that you have seen before. We're going to talk about that in a bit. But right now, if we follow this descriptions of W3, W3 is this. W3 is the collection of all the 2 by 1 matrices, which is our column vectors, such that you have that. And we found that it's obviously not empty. Easiest possible example is this. Okay, cool. Now, so let's take 2 elements from W3. So let's call one of the elements is P, all right? And one of the elements is Q, right? So from the context, you know that P is P1, P2, okay? It's in R2, okay? From the context, you know that Q is actually something that looks like Q1, Q2, okay, which is in R2, all right? All right, so there are not any elements in R2. There are not any elements in R2. They are the one that has some x here, such that the P will equals to AX, okay? So Q will be the things that has some y here, such that Q will equals to AY, right? Because in order to qualify to be in W3, it has to look like this. So if you say that Q is in W3, means Q will have to be AX for some kind of x, like the one that we saw just now. We have, so for our A, 1, 2, 3, 4, we know that 1, 3 is in it. So we know 1, 3 is in it because 1, 3 is the 1, 2, 3, 4 multiply the 1, 0. So so if you say that P is 1, 3, so then P is in the form of AX, where the X is 1, 0. So you can see that 1, 3, 1, 0. So if you say that you have a P in W3, then your P will equals to A of something. That something is what we call X. All right, that's how you read the set. Okay, cool. So now your P is W3 means that exists in X1, X2 in R2 such that you have this. Q in R3 means that there exists a Y1, Y2, okay, such that you have this. All right, now let's see whether or not the sum of these 2 elements, P and Q, is still in R3, okay? So it's still in W3, sorry. So now you have P and Q. So because P is this, Q is this, so and also A is a fixed matrix, and you have that matrix operations tells you that you can't factor out the A, and you have that. So now, so is P plus Q in W3 or not? Yeah, it is, because P plus Q can be written as A of something. All right, A of something. That something is X plus Y, but it's A of something. So we are actually collecting things that can be written as A of something, and P plus Q obviously can be written as A of something. So P plus Q is in W3. Follow? We are collecting everything that looks like A of something, right? So because the sum P plus Q is A of something, therefore P plus Q is in W3. Same thing with the scalar multiplications. So you have a constant, okay, and you have an element in W3, and so whether or not this product is A of something, and you can see from the computation, it is. Kp is A of something, and therefore Kp is in W3. Now this is actually, I mean, it looks weird to you, but you have seen this kind of concept before when you look at functions. So this is actually the image of a mapping. So for example, in high school, you have fx, right? You have a function fx equals to, let's say, x plus 1. So how do you define the image of that functions? Well, we call it y typically. So the image of the functions is all the y such that your y is equals to some fx, where x is in the domain of f. Remember that? So for example, in this case, okay, when we can see that 2 is actually in the image of f, because 2 can be written as x, which is our, so let me just write like this, f1, right? So they're collecting all the y such that y equal to some fx, right? So 2 is in the image of f because 2 is f1, right? So every time you pick an element here, you pick an element here, y, you know that it is some f of x. If you pick another element that's called s, then you know s is some f of something, let's call it fy. So we're actually doing this. Now, in order to make this thing clearer, we are looking at, we're going to look at another set, which is our W4. And our W4, okay, looks like this. It consists, so we are given a linear transformation. Again, we don't really know what that linear transformation is. What we know is that it is linear and it maps R2 to R3, which means it takes elements in R2, okay, and map it to R3, like that, okay? Now, so they are actually collecting all the TV. Now, obviously, TV will be in R3, so we are actually wanted to figure out whether or not W4 is a subspace of R3. So we have R3, and your W4 is actually subset of R3, and we don't really know whether or not it's just a subset or it is a subspace. Okay, so now let's see what kind of elements do we know. Now again, because we don't really know what T is, but we know T is linear. From the homework, you know that linear transformations takes the 0 in R2 and map it to 0 in R3. So because of these equations, you can see that because of these equations, we can see that 0, 0, 0 is in W4. 0, 0, 0 is in W4 because 0, 0, 0 is T of 0, 0, right? So we're looking at the image, basically, of T, of that transformation T. So 0, 0, 0 is in W4. So W4 is not empty. Unfortunately, this is the only thing we know. Because T is not known, it's just only linear. We don't really know how T actually looks like. So the only thing that we know is that the 0 in R3 is in W4. Therefore, W4 is not empty. All right. Whether or not it's a vector subspace of R3 or it's just a subset, well, depends on whether or not this W4 is closed under additions and closed under scalar multiplications. Okay, so let's pick an element P in W4. So it means that P will be T of some V. All right, same thing as the one that we have before in the previous example. They are the same thing. Okay, so if you have P in W4, then they should have some kind of V such that P will be equal to T of that V. Because in order to be in W4, it has to be in this form, right? Let me say that again. So this one, most of the description actually coming from here. Okay, so as I said in class, the sets builder notation, sometimes the descriptions, a lot of information is coming from here, like the previous 3 example. And sometimes most of the description is coming from here. Right, so this one, the most important information is about this guy. Right here is TV. So if P is in W4, so P will be something that looks like this. For some kind of V in R2, and for some kind of, if your Q is in here, your Q will be in this form. For some kind of W in R2. All right, so we are collecting, as you can see, we are collecting things that looks like this, right? So if you add up P plus Q, well, so it's TV plus CW, but because T is linear, you can write like that. So since we are collecting things that looks like this, so your P plus Q does looks like this. And you look at this 2 alone, your P plus Q does looks like this. Is really T of something. So your P plus Q is in W4. Simple as that. All right. Same thing for scalar multiplications. So if you have a constant k, you have a p from W4. So your kp will looks like this. And because it's linear, so you can bring the k inside and you have this. And since we're collecting t of something, and your kp is really t of something, right? So therefore your kp is in W4. Simple as that. So it's, as we can see, W4 is closed under scalar multiplications and closed under addition. So W4 is not only just a subset. W4 is not only just a subset of R2. W4 is actually a subspace of R. What did I said? Okay, so W4 is not a subspace of R, not just a subset of R3, but it is a subspace of R3. Okay, subspace of R3. Okay, that's that. Okay, one last example. The sets of polynomial of degree at most 2, right? We know that with the usual the polynomial addition and scalar multiplications, P2 actually is a vector space. And then now we are looking at W5. Though W5 is a subset of P2, okay, so it consists, so let's try to make sure you understand how this set looks like. So it looks like all the elements are like this, but A0 and A1 and A2 here, all the coefficients here are not any coefficient that you can think of. In fact, it is only collecting those elements, those polynomial, where the coefficients satisfy these descriptions. So in this set builder notations, most of the information is actually coming from here, not here, because we already know how it looks like in general, okay, but it's coming from here. Okay, so do we know any elements that is in W5? Yeah, we know the 0 polynomial is in it, because obviously, as you can see, all these entries add up to 0. That's a trivial one. And so we can find something else also. We can have 1 plus 1x and then minus 2x squared. This is also in W5 because the A0 and the A1 and the A2 add up equals to 0, right? So on and so forth. So there are infinitely many elements that looks like that in W5. So you know how W5 looks like. So now if you take 2 elements from W5, so this is one way you can do. You can kind of say, you don't really have to do it this way. I'm going to show you one alternative. But since P is in W5, so if you write P as A0 plus A1x plus A2x squared, we know that A0 plus A1 plus A2 has to be 0. So we can write the A0 in terms of A1, A2 if you want to. So you can write A0 as minus A1 minus A2. That's what you see right here. So I'm like substituting my A0 with this, okay, because they have to satisfy these equations. All right, so I'm doing the same thing for B. So for Q, so I have something that looks like that. So in fact, all the elements in W5 can be written as polynomial that looks like this and polynomial that looks like this. You don't really have to do it this way. I'm going to present you an alternative in a minute. But if you want to do it this way, you can, usually sometimes we want to do it like this because we are trying to say that we don't need 3 parameters. We can describe all the elements in W5 with 2 parameters, and those 2 parameters are the A1 and A2, and that's it. So I don't really need the third parameters. Okay, you will be very comfortable with this concept soon, but right now, it might be a little bit weird for you. Okay, so W5, P, W5 means P is like this, Q is like this. What happens if you add them? Well, after you add them, this is polynomial addition, you have this. And in order to see whether or not this guy here is in W5, we have to verify their coefficient had to add up to 0. So in this case, the coefficient, the constant terms is here, the coefficient for x is here, coefficient for x squared is here. So I'm adding, and I got them 0, obviously. So therefore, W5 is closed under additions. Same thing with scalar multiplications. It's pretty easy to show that. It's closed under scalar multiplications. Therefore, W5 is not only a subset of P2, but it's a subspace of P2. Now, if you're not happy with this, as I said, you can just basically do it this way. So P looks like this, Q looks like this. You take these 2 things from W5, then A0, A1, A2 is not any numbers. It's only those numbers, those 3 numbers that give you the sum equal to 0. Same thing here. If you take Q from W5, then your Q looks like this. And B0, B1, B2 has to add up to 0. And then you try to see what happens if you add them. And obviously, after you add them, you have things that looks like this. So whether or not this guy here is in W5, you will have to verify whether or not the coefficient here has to add up to 0. Now, why do we have to check whether or not those coefficients add up to 0? Because that's the main characteristic of all the elements in W5. In W5, it has to look like this. So we have to do whatever that set is telling us to do. And it can be anything. So I cannot give you infinitely many examples. I just have to let you know that the way to check is to read, to see what are the descriptions, what are the elements. So sometimes the information come from here. Sometimes the information come from here, but actually most of the time you actually have to use both, right? You have to use both to figure out what are the elements. So that's the reason why we are checking here that this, add it up. It's the same as adding all these three numbers and adding all these three numbers, and this is 0 because this is why P is in W5. This is 0 because that's why Q is in W5, and since it satisfied that, so the sum is really in W5. As simple as that. So it's closed under additions. And you can also show the same thing as closed under scalar multiplication, and that's it. And that's how you check, how do you verify that something is closed under addition, closed multiplication. You really have to pay close attention. No pun intended. You really have to pay close. I don't know how to say it another way. You have to be careful about what are the elements in the set. So you really have to look at what are the elements in the set. How do we describe that set? How do we describe W1? Okay, most of the things come from here. Okay, this is important too. How do you describe W2? Okay, this one tells you something. This one tells you something, but most of the information is here. Okay, how do you describe W3? Well, W3 looks like this. Most of the information coming from here. W4, most of the information coming from here. This is what it's trying to tell you. This is trying to describe what this thing is. And what is W5? W5, most of the information is coming from here. So you just have to make sure you know how to read the set. It sounded easy. We know sets a long time ago, but you kind of have to know what are the sets. How is the set looks like. Okay, that's basically it. Tomorrow we're going to start with the new sections, and hopefully this will help for those who say they need more example. All right. See you guys tomorrow. See you all tomorrow.